The most powerful testimonies often come from witnesses who cannot speak. In the eyes of the law, physical evidence is silent, but through the lens of chemistry, it speaks with absolute precision. Forensic chemistry and toxicology are not merely laboratory subfields. They are an integrated discipline that bridges the gap between complex biochemistry and the legal system. While they share a common analytical toolkit, their objectives diverge in fascinating ways. I am Anderson Worko. Welcome to the Forensic Chem and Tox Academy. And today on the Forensic Chem and Tox Academy, we are exploring the integrated disciplines of forensic chemistry and toxicology, the scientific bridge between the crime scene and the courtroom. The power of these sciences lays in their intersection. While a chemist identifies a lethal powder at a scene, the toxicologist quantifies that same substances within a biological matrix. This synergy transforms raw chemical data into a narrative of cause and effect that can withstand the highest levels of legal scrutiny. Whether you are a student, a legal professional, or a science enthusiast, prepare to see how we turn the invisible into the incontrovertible. Let's dive into the science behind the evidence. Forensic chemistry and toxicology science, an integrated discipline. Forensic chemistry and toxicology are two interlinked, specialized branches of forensic science. They apply the principles and techniques of chemistry and biochemistry to legal investigations, serving as a critical bridge between scientific analysis and the justice system. Their primary goal is to identify, quantify, and interpret the significance of physical evidence, to answer questions of what, how much, and sometimes why. Key areas of application: controlled substances and illicit drugs, analysis of powders, pills, plant material, and synthetic drugs. For example, cocaine, heroin, fentanyl, MDMA, to confirm identity, purity, and origin, or chemical profiling. Explosives and fire debris, detection and identification of accelerants in arson cases, and analysis of post-blast residues to determine explosive type. Trace evidence, analysis of small, often microscopic materials, such as paint from automotive collisions or burglaries. Fibers, textiles, carpets, clothing, glass, fracture matching, and refractive index analysis. Gunshot residue, detection of primer particles. For example, barium, antimony, lead. Ink and paper analysis, document examination for forgery detection. Environmental forensics, tracing chemical pollutants to their source. For example, oil spills, industrial contamination. Core techniques, separation science, gas chromatography, liquid chromatography, or high-performance liquid chromatography. Identification and molecular analysis, mass spectrometry, infrared spectroscopy, Raman spectroscopy. Elemental analysis, scanning electron microscopy, or energy dispersive X-ray spectroscopy. Inductively coupled plasma mass spectrometry, or ICP-MS. The forensic chemist question: what is this substance, and does it match that one? The second topic is, what is forensic toxicology? Forensic toxicology is the science of poisons in biological system. Core focus, the detection, identification, and quantification of drugs, poisons, and their metabolites in biological specimens to determine their influence on human behavior or cause of death. Key areas of application: post-mortem or death investigation. Toxicology determines if drugs or toxins contributed to or cause of death. Analysis of blood, urine, vitreous tumor, liver, and gastric contents. Human performance toxicology investigates the role of substances on impairment. For example, driving under the influence. Correlates blood alcohol concentration or drug levels with behavioral effects. Workplace and drug-facilitated crime toxicology detects drug use in employment settings or in cases of assault. For example, death rape drugs like GHB, flunitrazepam, doping control, detection of performance-enhancing drugs in sports. Core considerations and challenges. Metabolism. The body transforms parent compounds into metabolites. Toxicologists must often look for both. Interpretation. It is not just about detection, but interpretation. What does a 0.08 milligram per liter benzodiazepine level mean? Was it therapeutic, toxic, or fatal? This requires knowledge of pharmacokinetics, pharmacodynamics, and post-mortem redistribution. Specimen selection. Different drugs accumulate in different tissues. Blood shows recent exposure. Urine shows past use. Hair shows long-term history. Core techniques. Uses many tools from forensic chemistry. Gas chromatography, liquid chromatography, mass spectrometry, but applies them to complex biological matrices, requiring extensive sample preparation. For example, solid phase extraction, hydrolysis. The forensic toxicologist's question: was this substance present in the body? At what concentrations? What was its likely effect? Synergy in practice. The integrated workflow. A single case often requires both disciplines. For example, scene. A white powder is found at a death scene. Forensic chemistry identifies it as pure fentanyl. Autopsy. Blood is collected from the deceased. Forensic toxicology quantifies the fentanyl concentration in the blood at a lethal level. Conclusion. The integrated report states the cause of death was acute fentanyl intoxication, with the scene evidence providing context. Core principles and challenges. Chain of custody. A legally rigorous documentation process for handling evidence. Quality assurance or quality control. Adherence to strict protocols. Use of standards, blanks, and controls to ensure data integrity. Accreditation, for example, ISO or IEC 17025 is paramount. Validation. All methods must be scientifically validated before use in casework. Uncertainty measurement. Reporting results with defined confidence intervals or margins of error. Expert testimony. The forensic scientist must be able to explain complex scientific findings clearly, accurately, and objectively to judges and juries, distinguishing between scientific fact and interpretation. Modern trends and evolution. Novel psychoactive substances. The constant influx of designer drugs. For example, synthetic cannabinoids, catechinones, requires agile, non-targeted screening methods. For example, high-resolution mass spectrometry, microsampling, and minimally invasive techniques, dried blood spots, oral fluid testing, advanced data analysis, chemometrics, statistical pattern recognition for source attribution, ethical and legal scrutiny, increased focus on scientific validity. Following reports, like the NAS 2009 report, emphasizing methods, reliability and cognitive bias mitigation. Finally, conclusion. Forensic chemistry and toxicology are fundamental laboratory-based pillars of modern forensic science. They transform ambiguous evidence into objective chemical data that can corroborate or refute investigative hypotheses. Their strength lies in rigorous scientific methodology, continuous adaptation to new analytical and legal challenges, and the integrated interpretation of chemical findings within a medical legal context. They are, in essence, the science behind the evidence that speaks,